Hello, Calculus Beasts. Welcome back. So your first assignment on our virtual learning is you guys are going to practice what we were doing at the very end of class right before we left for spring break, which is solving these differential equations when you're given a dy dx or given a derivative. If you look at the guided practice, we're going to do two questions together. The first one is gives us our dy dx, and it says sketch a slope field. So because I have dy dx, to know what the slope is going to look like, all I have to do is plug into dy dx, because this right here represents the slope. So I always start with where does the slope 0, because I know like sketching a slope of 0 is really easy. It's a flat line. So if I'm looking here, in order for dy dx to be 0, that could be when x equals 0 or when y equals 1. Then I'm going to get my slope is 0, because that x equals 0 makes this term 0, and y is 1 makes 1 minus 1 0. So I'm going to go to x equals 0. So x equals 0 is in here. And then y equals 1, go to y is 1, here and here. And then now I only have 1, 2, 3, 4, 5, 6 points that I actually have to plug in for. So this point is 1, 0. So 1, 0, and you can just literally plug in 1, 0. So that would be 1, 0 minus 1 over 4. So this is negative 1 over 4. Yeah, I did that right. So negative looks like this, and 1/4 means it's not very steep, so something like that. If I go over here, this is the point negative 1, 0, so that's negative 1, 0 minus 1. That's negative times negative makes positive 1 over 4, and then positive 1/4. Positive slope is increasing, but 1/4 means it's not very steep, so I'll make that. Those are supposed to be of the same steepness, just opposite directions. This point is 1, 2. So then 1, 2, plug in. 1, 2 minus 1 over 4. 2 minus 1 is 1, so this is just 1/4, so positive 1/4. Not very steep. This one is negative 1, 2. The only difference is there's a negative sign right there, so this is negative 1/4, so like that. And lastly, this is 1, 2, 3. So the point 1, 3 is 1, 3 minus 1 over 4. So that's 2/4. So not as shallow, a little bit steeper than before. And then this one, same idea. Okay. Part B, it says, let y equals f of x be the particular solution to the differential equation with the solution f of 1 equals 3. So I have the point 1, 3. Write an equation for the line tangent to the graph at that point and use it to approximate f of 1.4. So first, let's just write the equation of the line tangent to the graph of f at this point. So we have y minus y1, which is just the 3, equals slope, I'll come to that in a second, x minus x1, which is just 1. So I use my point to plug in, and now, not pointing correctly, and now I'm just plugging in to get my slope. My slope is just going to be the dy dx. So I'm going to find what dy dx is when we are looking at the point 1, 3. So that means x is 1, y is 3. 3 minus 1 is 2, so this is 2/4 or 1/2. So then that's my slope, 1/2. Now I have my equation of my tangent line, and it says use that to approximate what f of 1.4 is. That means I'm going to plug in 1.44x. 1.4 minus 1 is 0.4. Half of 0.4 is 0.2. Add the 3 over, so y is approximately 3.2 when I'm looking at the approximation for f of 1.4. My tangent line, and then the approximation I used my tangent line to get. Right, part C is actually solving to find the solution to the differential equation. So again, I have my dy dx and I have my point. This is what we were doing the last day with the separate, integrate, plus C, plus C, plug it in, solve for y. Oh man, been a minute since I sung that. Alright, so when we say separate, the idea is we want to get anything that has an x on one side, anything that has a y on the other side. So here I have both x and y, so I'm going to multiply both sides by dx to move that over. So now I have dy is x, y minus 1 over 4 dx. This y minus 1 factor I can divide over. So that's gone. So we have dy over y minus 1 equals, that crossed off, so this is x over 4, but I'm going to write it as 1/4 x just because I like to have my coefficients like that, not in over 4, but a 1/4 coefficient. All right, now I have them separated. Next step is to integrate. Okay. This side should be easier. It has been a while since you've done an integral, so remember the idea is you add 1 to the power and then divide by that number. So here x would become x squared, and I need to make sure I divide by that power, and there's still a 1/4 out front. So 1/4 divided by 2 would just become 1/8 x squared. I have to have my plus c. Now on this side, you could rewrite it as like y to the -1 power, y minus 1 to the -1 power. If you add 1 to this, you get to the 0th power, which doesn't make any sense. So that's where you go, oh yeah, this is just going to be natural log, because very similar to the 1 over y, this is 1 over y minus 1, so this is going to be natural log of y minus 1. Technically, anytime you do natural log, it is an absolute value because you can't take natural log of a negative number. So then this is just natural log of y minus 1. And 1/8 x squared plus c. You have to have the plus c. Remember, that's the separate, integrate, plus c. And now we plug in to get that c. So we have our 0.13. 1 is the x. So this is... And then 3 is the y. This is natural log of 3 minus 1. 3 minus 1 is 2. So this is natural log of 2. And equals 1/8 plus c. Subtract the 1/8 over. So natural log, natural log of 2 minus 1/8 is my c. And now I just going to rewrite everything. So this is natural log of y minus 1 equals 1/8 x squared plus c, which is natural log of 2 minus 1/8. I need to get the y by itself, so I need to get rid of this natural log. To get rid of a natural log, you do e to the power. So this just becomes y minus 1, and this is e to the 1/8 x squared plus natural log of 2 minus 1/8. Now we can simplify this, so this is adding in your exponents is the same as if you had multiplying, so 1/8 x squared times e to the natural log of 2 times e to the -1/8. Now e to the natural log of 2, that can just become 2 because e and natural log cancel out, so this is times 2. But there's nothing you can do about this, so I'm just going to call it e to the 1/8 x squared minus 1/8. And then we have not gotten y by itself, so the last step is you need to add this 1 over, and there's your answer. I'll rewrite this neatly, actually. So y equals 2 e to the 1/8 x squared minus 1/8 plus 1. And just making sure it is very clear that this is all in the exponent and the plus 1 is not in the exponent. And that's our solution. We separated, integrated, plus c, plugged in to get c, and then last step was solve for y. Okay, number 2. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt is 1/25 W minus 300 for the next 20 years. W is measured in tons, T is measured in years from 2010. So they gave me this. They didn't give me the point necessarily in this form, but they did say at the beginning there was 1,400 tons. So that is the point when T is 0, W is the 1,400. That's where I got that. It says use the line tangent to the graph of W at T equals 0 to approximate the amount at T equals 1/4. So first we'll just use the tangent line at t equals 0. So I'm going to use the tangent line at this point. So y minus 1400 equals slope x minus 0. Now, just like before, in order to get the slope, I can just use the derivative. So I want dw dt at the point 0, 1400. So this is 1/25. And now I need to plug in w minus 300. A lot of you might be tempted to plug in 0, but this is really like my t, and the y is like my w, right? So this, when I'm plugging in dw dt, it's not 0 for w, it's the 1400. Minus 300. 1400 minus 300 is 1100. Divided by 25 is, divided by 25 is 44. So this right here is my slope because I plugged into my derivative to get it. So 44. That is the first part. I've written the equation of the tangent line, and it says use the equation of the tangent line to approximate the amount of waste at the end of the first 3 months, which is t equals 1/4. So now I just plug in 1/4. 1/4 of 44 is 11. And last step is add that 1400 over. So then y would be approximately 1411. That would be the amount of waste, or the w, I guess, is like the y in this case, at t equals 1/4. All right, B says find the second derivative in terms of w, and then we'll answer based on that. But first, let's find the second derivative. So I'm going to go to the first derivative and take the derivative of that. So 1/25 is just a coefficient, right? You don't need to do anything with that, just carry it over. The derivative of w would be dw dt, so we're taking the derivative with respect to time, and then the derivative of minus 300 is just going to be nothing, right? It's just a constant, so it goes away. Now, some people are tempted to leave it like this. That would be incorrect because it does say find the second derivative in terms of w, not in terms of dw dt. So what we need to do here is take our dw dt, where's my red pen, and substitute it in, you got a colored pen, substitute that in for dw dt. So this is dw dt right here, take it and substitute it in. So this is going to be 1/25, dw dt is 1/25 w minus 300. Now you can absolutely leave it like that. I like to just clean it up a little bit. Oh wait, no, I don't know what 1/25 times, I don't know what 25 times 25 is. Never mind, I'm gonna leave it like this. That's my answer. And then it says use this to determine whether your answer in part A is an under or an overestimate. To find what the w is at t equals 1/4. So here, I always sketch the graph for the over and under, similar to when we had the Riemann sum, right? You just sketch a right Riemann sum, and then whether it's increasing or decreasing tells you whether it's whether it's over or underestimate. So what this tells me, second derivative, so this tells me that my second derivative is positive, right? Positive times positive is positive, as long as we don't have less than 300, which it's starting at 1400, so we're good. So the second derivative is positive, and it tells me in the question that the function is increasing. So second derivative is positive, and w is also increasing. Second derivative positive means w is concave up. So I know that it is both concave up and increasing. So then what I'm going to do, I'm going to sketch concave up. Increasing is just this part right here. Now, I used a tangent line to approximate something, so anywhere where it is increasing and concave up, doesn't matter where, I'll just point like kind of in the middle. If I use a tangent line like this is my tangent line. If you look, a tangent line approximation is going to be an underestimate. See how my green line is going to be below what the graph, the blue line is? So then your approximation from part A is an underestimate because the second derivative is positive, which means W is concave up. And if you look at the graph, concave up and increasing, your tangent line is in under approximation.